Greetings, peeps! Projectile motion with the first scenario, which is the Halfabola situation. Okay, let's look at what we got here. A Flugtagus is rolled to the edge of an 8-meter pier. The center of gravity is 1 meter above the wheels. We saw center of gravity and the fact that the center of gravity will always go in a parabolic arc when you jump, no matter how you move the rest of your body. So we saw that with the hang time clip and basketball players. So what we want to know is, with this Flugtagus being rolled horizontally off the edge of a pier, how far away from the pier, delta x, will the Flugtagus make a splash in this water? What is the craft's final velocity just before impact? And so I've drawn out the situation here. Here's the Flugtag machine. You don't know what Flugtag is? Well, you should either look it up, or we'll actually go over Flugtag in class. But it's a pretty wacky contest where people come up with so-called flying machines that are thrust horizontally over a pier, and they measure how far it goes. The furthest from the pier wins. So in this case, we have some information about this particular machine. It's got some wheels and it's being pushed in this direction at a velocity of 12 meters per second. The height of the pier to the water is 8 meters, but we're told that the center of gravity, which is what we're interested in, is 1 meter above the wheels. So we have a total of 9 meters. So delta y really is 9 meters, even though the pier is 8 meters tall. And I've got my coordinate system set up here so that we know the up direction is positive for y, to the right is positive for x. We want to know what this range is, delta x. How far is the Flugtag going to go in this characteristic Halfabola pattern? We also know one more piece of information, and that is the acceleration in the y direction, because of our coordinate system, is negative 9.8 meters per second squared. So we're going to take a look at how to solve this. First, our matrix of variables. Hey peeps, and so here is your matrix of projectile motion variables. What I've done is actually color-coded them so that you can understand what is a known value for any situation and what comes from values that were given to us in the situation depicted before with the Flugtagus. All right, so in black ink is where we absolutely know the value every time. For example, AX, because there's no horizontal gravity, will always be 0 meters per second squared. Vy peak is always going to be 0 meters per second squared. Well, what does that mean, Vy peak? Well, if you throw an object upwards, it's going to, due to the negative acceleration, or acceleration in the opposite direction of motion, it's going to slow down until it reaches its peak, where it's absolutely at 0 meters per second at the apex, okay? So if you toss something straight up, it'll just go to its maximum height and then back down. Or in the case of the objects here, we're going to throw it up and maybe at an angle, and it's going to be the top of the parabola. So Vy peak is known as 0 meters per second. We also know the acceleration due to gravity on the surface of the Earth, and that's negative 9.8 meters per second squared. Again, the negative comes from the fact that our coordinate system says that up is positive for y, and to the right in this case is positive for x. So that's what determines this negative. But the value is 9.8 meters per second squared, so black ink. In blue ink is given information. All right, so we'll start over here that we had an angle of 0 degrees. It wasn't told to us, but we know that because the object is moving horizontally, all that motion is going to be horizontal until it reaches the edge of the cliff. And so the angle relative to horizontal is 0 degrees. It's not tilted upwards from the horizontal at all. And Vx naught is 12 meters per second. So if we go to the share combined values, theta equals 0 degrees, V naught is 12 meters per second. Okay, so if we go to Vx naught, which is the same thing as Vx. Why is that? Again, because there's no horizontal acceleration. There's no horizontal gravity. So these two are equal. That's the same velocity. It's a constant velocity in the x direction. So it's equal to V naught times the cosine of the angle theta. Cosine of 0 degrees is 1, so therefore all of this velocity here is going to be translated into horizontal motion, 12 meters per second right here. Whereas Vy naught is V naught times the sine of the angle. Sine of 0 degrees is 0, and so there's no vertical motion until we leave the cliff. And that makes sense because the surface is supporting that object that's rolling, in this case, the Flugtag machine. And it's not going to be falling until it leaves the edge of the cliff. All right, so there we go. So now we've got all of our variables. What about a strategy? Here we go. In order to get delta x, so you see, notice the red question marks. That's the first thing we're going to get. That's the range. And later, what we want is v. We need to get certain information. And the strategy would be to use this information, the data, and kinematic equations of motion, so they're coming back, to find time in the air and share with the xy pair. Whoa, that sounds kind of funky. The strategy is to find the time of the flight, and therefore we can share that with the other side. You might find the time from the horizontal side, but in order to do that, you actually need all pieces of information here, and we're missing delta x. So therefore it tells you automatically that you're going to find time from the free fall event, knowing we have information from the y side. So because objects dropped and projected horizontally at the same time, will land at the same time, we can rely on the y side, due to the independence of perpendicular vectors, to come up with time. All right, so that's what we're going to do. The strategy is to use one of the sides, in this case the y side, to find time and share it with the x side. So that's what it is, to share with the xy pair. Let's do that. So let's do it. Let's find time from the y side in free fall motion. Okay, so here we go. To reiterate from before, although you probably have the matrix in front of you because you copied it down from before because you are good note takers, okay? So what I'm relying on you to do, because as problems get more complex and layered, you're gonna have to keep track of that stuff because I only have so much room here to show you, so I rely on you guys to kind of keep that stuff, all right? So you will have the matrix in front of you, but I did kind of summarize what we need, and that is delta y is -9 meters, Vy peak, as discussed, is 0 meters per second, Ay -9.8 meters per second squared. So we want to solve for t in this case. Well, I've got a couple equations with t. That's the first one and the second one. And the one that's more valuable is this one here because I don't have Vy, so I need to use this equation to do it. But it's not so bad because notice here that I have delta y, I have Vy naught, and I have Ay, so I can solve t. If I had a Vy naught value, which I do, it's 0, if I had an actual value, then I would need to solve this using the quadratic equation, a t squared term, a t term. It's fortunate though that this term is 0 and just disappears so that we can solve it more easily just with a simple square root function. So I did the algebra and we get t equals 2 delta y over Ay. And so if I crank this through, we get square root of 2 times -9 divided by -9.8. Anyway, 1.36 seconds is the term over here. All right, so we have the time of the fall to the water. That's excellent. So now we can find delta x from horizontal data and t. To reiterate some of the information kept on the the horizontal side, Vx naught is 12 meters per second, Ax is 0 meters per second squared, and now we got time. It's 1.36 seconds. So I choose this equation, the second equation here, because it already has delta x, right? So I check the variables I have, Vx naught, t, and this term goes to 0, so I don't have to even work with it. And so if I solve here, delta x is already solved, which is cool. I get 12 meters per second times 1.36 seconds is 16.32 meters. That's how far away from the pier the Flugtag will land. Okay, I also decided to write this over here because sometimes in advanced physics, you are required to solve in terms of other variables with no numbers. You'll just say, solve in terms of given variables like delta y, Ay, and Vx naught. Okay, so here's what this is. It's delta x in terms of Vx naught, that's over here, times t. And here's the expression for t, so I just substituted this down here. And we get this whole expression here that resembles delta x. And so sometimes you'll be required to just use symbols, and this would be your final answer for time. Boom, right there. So that we can change any of the variables and see what the situation might be. So just wanted to give you a little preview of what's possibly to come. But for now, we can use the number calculated for time, and thus we get an actual displacement away from the pier, 16.32 meters. Let's get that final velocity as the object is about to hit the water before impact. Very important, before impact, and I'll explain why coming up next. So let's find the velocity of the Flugtagest just before impact. And why do I say just before impact, that infinitesimal moment just as it's about to hit the water? Simply because we don't have the physics yet to take care of the collision between the Flugtagest and the water. Because you might be tempted to say, well, the final velocity, of course, is 0. Well, it's not 0, not right away, not without some interaction with the water or whatever you're colliding with. So that's an important thing, and we just don't have the physics to handle that collision in order to figure out, well, what happens in order to get the Flugtag velocity to 0. So really, what we're looking for right now is just that moment where the velocity is just before the impact, and that's what we can handle at this point. And it's curious to know, well, how much velocity did it pick up due to falling, all right? Well, in order to do that, since we're talking about falling, is that we need the Vy. And so equation 1 or equation 3 from your kinematic equations of motion will suffice and solve for Vy. So I've produced the values here again, but of course you're keeping them nice and tidy in your own matrix somewhere else while watching this. So delta y is -9 meters, Vy naught again, 0 meters per second, Ay, -9.8 meters per second squared, and the time we have now, we can use it, is 1.36 seconds. Now I'm going to solve this both ways just to show you that it can be done. It comes up with the same result. We have the first equation, which is Vy equals Vy naught plus Ayt, and Vy naught is 0, so it goes 0, goodbye. Vy equals -9.8 meters per second squared times the time, 1.3 seconds. We get a vertical velocity, just the vertical velocity. This is not the final answer. This is part of the answer. 13.3 meters per second. What if we use equation 3? Well, it looks like this. We didn't have to have time. We could have used our original information and gotten the velocity without even figuring out the range, which is interesting. So we got Vy squared equals Vy naught squared plus 2Ay times delta y. So this term is 0. So Vy is the square root of 2Ay times delta y. Cranking this through, not surprisingly, it comes up with the same result. Due to rounding errors, they're not exact, but actually to this decimal place, they are. So within 3 significant figures, 13.3 meters per second, 13.3 meters per second. Happy, happy. Here's what we got to do to find the final velocity. All right, here's a picture of it just before impact. We want to find the green vector v, which is the total resulting velocity. Well, remember before, this thing is traveling horizontally as well at 12 meters per second, and it's traveling downward. Now, do this calculation at 13.3 meters per second. We got to find what this is, and basically this becomes a right triangle, or the trig comes back, and so we use the Pythagorean theorem here. V equals the square root of Vy squared plus Vx squared, and we get a total of about 17.9 meters per second. Gut check, that's the hypotenuse, and that is greater than either of the two sides, the adjacent or the opposite, so we're looking good there. All right, I feel good about that value. If it was way, way high, like more than the sum of these two, the 25.3, I'd feel bad. And if it were less than any of these two values, I'd feel really bad. It's right in that range, so I feel pretty confident. So that's the gut check. What about the angle? We need to know at what angle it crashed into the water to the center of gravity, that is. And the angle of impact, which is not the theta from the beginning, but the angle of the impact is going to be related to the inverse trig function here. I like tangent a lot because we calculated the hypotenuse, and you can use any function from there, but these are the ones that we already have. So it's the opposite side Vy divided by the adjacent side Vx. So inverse tangent of Vy divided by Vx gives you an angle about 48 degrees, and that's, my gut check says that's about right, because if these were equal, they'd be about 45, that would be exactly 45 degrees, and they're not far off. 12 and 13.3, they're pretty close to each other, so the angle is not far from 45 degrees. Another great gut check, and I think we got it. So what I'm gonna do very silently, I'm gonna sign off here, but I'm gonna put another screen in there so you can see the final matrix of this entire problem. All right, I bid you adieu. Morad out.